Hey everybody, this brief lesson is about resistance in wires. And what I'd appreciate is if you could pause the video after this question is asked, but what characteristics of a wire, and we're only going to do circular wires, but what characteristics of that wire do you think would affect its resistance? So maybe pause the video and just think for like 30 seconds. What might affect the resistance in a wire? And now you're back, and I don't know if you paused it or not, but hopefully you came up with some obvious things like length of the wire. Think about it, the more the electrons have to get through, probably, there's going to be a difference in resistance. Also, maybe what the material is. What is it made of? Is it made of copper? Is it made of tungsten? Is it made of gold? Who knows? And also the diameter. But we're going to say, you might have said diameter or thickness, but we're going to say the area of the wire, and that's the cross-sectional area, which will always be circular. So for us, it will always be pi r squared. Now, we could do problems with square wires and hexagonal wires, but we're just going to stick with those three things. And the area will always be of a cross-sectional area of a circle, which will be pi r squared. Now, the material is known as rho, which is it's Greek letter rho. It's not a P, and it's called resistivity. Resistivity, and it's measured in ohm meters. That's ohms times meters. Ohm meters. I know, weird unit. And length is obviously measured in meters. So I was wondering if you could pause the video really quick and think about length and area. Just a quick question to yourself. If the length increased, what do you think happens to the resistance? And if the area increases, so now think about having a wider hallway and you're trying to get to class, what would happen to the resistance? Maybe pause the video and think for a second. So now you're back, or you never left, I'm not sure. And this is basically just like it's a simulation. We were debating doing a lab. We're definitely not doing a lab, but hopefully you guessed. As the length increases, so would the resistance. Look, hence it's in the numerator. It's not the greatest of apps, but you get the idea. And resistivity, the larger the resistivity, the larger the resistance, and vice versa. So that's going to be in the numerator. And finally, hopefully you correctly guessed that if there's a larger cross-sectional area, there's more room for electrons to move, and therefore there would be less resistance. Hence, it's in the denominator. So hopefully you noticed that in that simulation kind of thingy, there was already an expression there for you for the resistance of a wire. So the resistance of any wire is equal to rho times the length over the area. And please remember that the area is the area of a circle. So we're going to do a quick sample problem to see how this goes together. Okay, so supposedly there's we'll say a 10-volt source, and there's a wire that connects to a resistor and another wire that comes back to the other side of the battery. We're going to say that the first wire is made of 2 meters of copper and that it connects to a resistor of 10 ohms. And then the other wire will go with 3 meters long and made of tungsten. So, excuse me. One thing you should be aware of, we haven't considered the resistance of these wires at all. So if we wanted to know the current in this little circuit here, normally we would just do the current coming from the source is equal to the voltage, oh my God, I said velocity, voltage of the source over our equivalent, which is, I'm sorry to even do the math in front of you because I'm sure you can do it, 1 amp. So if we don't include the wires, it's 1 amp. But the wires do have resistance. And unfortunately, we're not doing these hands-on labs where we could actually quantify this, but okay. So some information we can do for this problem, we'll say that the radius of these wires is 0.5 millimeter. Yes, we're going to convert that to meters. The resistivity of tungsten happens to be 5.6 times 10 to the negative 8 ohm meters. The resistivity of copper is 1.68 times 10 to the negative 8 ohm meters. So we have to spend a second here and figure out the resistance of each wire. So I'm going to do that on the left here. I'm just going to use this expression that we have, our new one here. So the resistance of the tungsten wire would be rho, or resistivity, which is 5.6 times 10 to the negative 8 ohm meters, times 3 meters long of wire, all over the cross-sectional area, which is pi times the radius squared, which is half a millimeter, or 0.0005 meters. Don't forget to square. And we're going to get a resistance of 0.24 ohms. I have to do the same thing with copper. So the resistance of the copper wire is its resistivity, which is 1.68 times 10 to the negative 8 ohm meters, times its length, which is 2 meters, over the same cross-sectional area, pi times 0.0005 meters. Don't forget to square because everybody does. And that will give us a resistance of 0.043 ohms. Now, one of the things I want you to realize is that if you trace the current flow from one end of the battery to the other, you'll notice it goes through the copper wire, the resistor, then the tungsten wire, and it comes back. So basically, these three elements are in series with each other, which means we just add all the resistances together to get the total resistance. I promise all the problems that we do will just be wires and a resistor in series. We'll keep it pretty straightforward. So that means that the equivalent resistance of this circuit is actually the resistance of the copper plus the 10 ohms plus the resistance of the tungsten wire. So our equivalent is the copper was 0.043 ohms plus the 10 ohms plus 0.214 ohms gives us a total resistance of the circuit of actually 10.257 ohms. So now if we really wanted to know how much current was flowing in the circuit, including the wires, we get that the current coming out of the source is the voltage of the source over R equivalent. And in this case, that's going to be 10 volts over R equivalent, which includes the wires now. And we get that it's 0.975 amps. So it's a little less than what we had expected originally, which would have been 1 amp. So that's how we include resistance of wires in our problems. It's pretty straightforward. It's a new expression. You kind of substitute and solve. Just watch the squaring on the bottom. Watch how you enter this in your calculator. Please remember, if you're dividing by pi r squared, you want to put the entire denominator in parentheses. Otherwise, you will divide by pi and then multiply by radius squared. So please make sure you're entering it into your calculator correctly. Other than that, if you have any questions, you know where to find me, and I hope you're all well.